Calculus video 57, the importance of linear approximation. So we've discussed linear approximation in the last couple of videos, but why is it so important? Well, the idea doesn't stop. The idea of estimating a curve doesn't stop with just lines, right? So what we're going to try and do here is expand the approximation of a curve by a line. That's what we've been doing, linear approximation. We're expanding the approximation of a curve by a line to the approximation of a curve by a higher degree polynomial. In other words, we've estimated, like one of our examples was f of x equals sine of x. We've estimated sine of x by the line L of x equals x as long as x is pretty close to 0. It's a pretty decent approximation. But can we get a better approximation for f of x equals sine of x than just a line? What if I used a polynomial instead? A higher degree polynomial. What if instead of a line, I used a quadratic? Or degree 3 polynomial, or degree 4 polynomial, or degree 5 polynomial? We want to take this idea of linear approximation, right, approximating by a line, and expand it to approximating a curve by a polynomial. So, thinking of that same function sine of x, is there a polynomial of higher degree that will approximate f of x equals sine of x better than our linear approximation L of x equals x? Maybe so. The idea of that is called Taylor polynomials. Polynomials that approximate other functions. And why might those be useful? Well, there are functions like sine of x that can be sometimes harder to work with. Whereas if we can estimate sine of x by a polynomial, polynomials are easy to work with. They are continuous everywhere. They are differentiable everywhere. So is sine of x, but this also applies to other types of functions. We can take the derivatives of polynomials rather easily using the power rule. We can integrate. If you haven't done that yet, you'll find out you can integrate polynomials rather easily as well. So their polynomials are easy to work with, and so if we can use one of those to approximate a more complicated function, sometimes that ends up being quite useful. Okay, so here's the idea behind this. You'll see this in a later calculus class as well, but it really does connect to linear approximation, so I like to introduce the idea here. So our linear approximation, in general, was the equation of the tangent line created at a f of a, and is given by, earlier I wrote this as L of x, but for consistency's sake here in this next argument, I'm just going to call it f of x. F of x, the linear approximation, is equal to f of a. I probably shouldn't use f of x there. Let's switch that to say g of x. That way I'm not necessarily talking about the same function. G of x is equal to, our linear approximation is equal to f of a, the value, the function value at a, plus f prime of a, the slope at that point a, f of a, times x minus a. The linear approximation, that's what we've been working with. But let's go up a degree. Is there a quadratic that will approximate our functions even better? Quadratic approximation. Okay, a quadratic approximation will look like this. G of x is equal to fa plus f prime of a times x minus a. That should look familiar. It's the same as the linear. Then we're going to add one more term to that. And I'm not going to describe in this particular video how we're creating these terms. That will come in a later video for probably Calculus 2, maybe Calculus 3, depending. But we're trying to recognize patterns here. We're trying to get some pattern recognition. So it's f of a plus f prime of a times x minus a plus f double prime, second derivative at a, divided by 2 times x minus a squared. Now we see that we have a quadratic here, where the coefficient of the quadratic is the second derivative at a divided by 2. That would be the quadratic approximation. Let's see if you can come up with the degree 3 approximation. If I was thinking, instead of g of x, I may have used p of x to represent polynomial here. I'm going ahead and switch mine. Polynomial function in terms of x. Degree 3 polynomial approximation, p of x is equal to, same thing it was for the quadratic, f of a plus f prime of a times x minus a, there's your linear, plus f double prime of a divided by 2 times x minus a squared, plus, now the degree 3 term, f triple prime of a, third derivative, at a, divided by 6 times x minus a to the third. And at this point you might be thinking, well, a couple things. Where did the 6 come from? But you also might be thinking, we could keep going. We could get a degree 4 polynomial approximation, degree 5, degree 6, degree 7, and one would think that the higher order polynomials would be a better approximation. It allows for more curvature than just a line does. Right? That's the idea of a Taylor polynomial, that we could continue doing this and have degree 5, degree 6, degree 7, degree 42 polynomials as an approximation for a function. Okay, let's try this. Let's try this for f of x equals sine of x. Now we already remembered that the linear approximation for this is just x. But let's see things we need for this. And again, let's start with a equals 0. So we're centering this around a equals 0. So we need f of a, we need f prime of a, we need f double prime of a, we need f triple prime of a. We need some derivatives evaluated at a, our a here being 0. So we know that f of x is sine of x, f prime of x is cosine of x, derivative of sine is cosine, f double prime of x, second derivative of cosine is negative sine of x, and f triple prime of x, derivative of negative sine is negative cosine of x. And we will be evaluating these at 0. F of 0, f prime of 0, f double prime of 0, f triple prime of 0. That would be the sine of 0, the cosine of 0, negative sine 0, negative cosine 0. The sine of 0 is 0, the cosine of 0, 1, negative sine 0, still 0, negative cosine 0, negative 1. Alright, so f of 0 is 0, f prime of 0, 1, f double prime of 0, 0, f triple prime of 0, negative 1. Let's plug those numbers into this degree 3 polynomial approximation. And let's see if I left myself any room here or not. I'm going to try and squeeze it in right here so we can kind of watch what happens. So the polynomial approximation, p of x, degree 3 polynomial, you might see like p3 of x to denote that this is a degree 3 polynomial approximation. F of a, that was 0, plus f prime of a. F prime of a is 1 times x minus 0, plus f double prime of a, that would be 0, over 2 times x minus 0 squared, plus f triple prime of a, that would be negative 1, over 6 times x minus 0 to the third. And if we wrote that out, we get, I'm going to go down here, p3 of x is equal to 0 plus 1 times x is x. That's our linear approximation. The quadratic approximation portion, that term, that drops off because 0 divided by 2 is 0 times anything 0. So that part's gone. Plus negative 1/6 times x minus 0 to the third. So minus 1/6 x to the third. And this is a degree 3 polynomial approximation of f of x equals sine of x. So I drew a couple graphs on decimals, so I just want to import those real quick. We've seen the one in a previous video where I've drawn f of x equals sine of x, and then f of x equals x, which is that linear approximation, looks something like this, right? Here we have f of x equals sine of x, and here we have the polynomial approximation of degree 1 is simply equal to x, or y equals x. And again, pretty good approximation from like negative 0.5 to 0.5. Let's look at what would happen now if we use the degree 3 polynomial approximation for sine of x. If we used, instead of just x, but x minus 1/6 x to the third. All right, let me bring that in. Okay, here we go. We have, again, y equals sine of x, or f of x, I guess I was calling it. F of x equals sine of x. And now P3 of x is equal to x minus 1/6 x to the third, which does look like a negative degree 3 polynomial, which it is. But now it's an even better approximation. If you can tell here, it's a better approximation for the graph of sine of x. It extends with a little bit of a curvature here. It's a good approximation for the sine of x. You can see all the way to basically 1 and negative 1, right? While the line was just a good approximation between like negative 0.5 and 0.5. We are around 0, around our center of 0, expanding, moving out, making it wider, the portion of the graph sine of x for which our polynomial is a good approximation. Whereas the linear was from negative 0.5 to 0.5, the degree 3 polynomial is a pretty good approximation from negative 1 to 1. And so the question now is, well, what if we keep going? What about a degree 4 polynomial, or a degree 5 polynomial, or a degree 6 polynomial, degree 7, right? What if this keeps on going? How close of an approximation can we get? Well, let's take a look at this. Again, we're just going pattern recognition here. We had, for the degree 3 polynomial, p of x is equal to, I'm looking at right here, p of x is equal to f of a plus f prim of a times x minus a, plus f double prim of a divided by 2 times x minus a squared, plus f triple prim of a divided by 6 times x minus a cubed. Can we keep this going? Can we get what's the degree 4 term? What's the degree 5 term? What's the degree 6 term? Let's go all the way out to degree 7 term. Well, what do you think the degree 4 term will be? By pattern, we think that instead of f triple prim of a, the degree 4 term would be the fourth derivative of a. But what do you divide it by? Where are we getting the 6 and the 2? That comes from the denominator here is whatever exponent we had on the polynomial. For instance, in this case it's 2. It's actually 2 factorial. And 2 factorial is 2 times 1. It's itself times every number below that till you get to 1. So, for example, 3 factorial, which is where the 6 is coming from, is 3 times 2 times 1. Right? 4 factorial, 4 times 3 times 2 times 1. 5 factorial, 5 times 4 times 3 times 2 times 1. That number is actually, whatever the exponent is, factorial. And so instead of 6 here, I could have written 3 factorial. Because 3 factorial is 3 times 2 times 1, 3 times 2 is 6, times 1 is 6. And then we're multiplying that by x minus a to the power of the next higher degree polynomial. So the next one will be to the 4th. So thinking of that pattern, we have a 4th degree polynomial. P4 of x is equal to f of a plus f prime of a times x minus a, plus f double prime of a over 2 factorial, I'll use the factorial notation here, times x minus a squared, plus f triple prime, the third derivative at a, over 3 factorial, times x minus a cubed, plus the fourth derivative, and that we stop using the primes because there's too many to kind of gets in the way. You lose track of how many primes you have, and we use this number 4 in parentheses to represent the fourth derivative at a over 4 factorial times x minus a to the fourth. Okay, 4 factorial, that's 4 times 3 times 2 times 1, that's 12 times 2 is 24. Okay, plus, let's keep going. Well, that's the degree 4 polynomial. Let's go all the way out to, say, the degree 7 polynomial. And this may take a little bit of room. That is f of a plus f prime of a times x minus a plus f double prime of a over 2 factorial x minus a squared plus the third derivative at a over 3 factorial x minus a to the third plus, and just to save some space, I know I'm going to need a second line anyway here, so let's go ahead and drop down the fourth derivative at a over 4 factorial x minus a to the fourth plus the fifth derivative at a over 5 factorial x minus a to the fifth plus the sixth derivative at a over 6 factorial x minus a to the sixth plus the seventh derivative at a over 7 factorial x minus a to the seventh. And you might be thinking, that's a lot of stuff. That's going to take me forever to plug that in. Well, it turns out it's not so bad in the case of the function being sine of x, because we get this repetitive pattern. Go back up here to the derivatives of sine of x. Your function is sine of x, the derivative cosine of x. That derivative is negative sine of x, and then the third derivative negative cosine of x. What's the fourth derivative? What's the derivative of negative cosine of x? That would be positive sine of x. The fourth derivative goes all the way back up to here to the top. The fourth derivative, let's do this in blue, is back to your original function. The fifth derivative is the same as the first derivative. Sixth derivative, the same as the second derivative. And the seventh derivative, the same as the third derivative. And so we get this pattern where f of a is 0, if we're plugging in 0 here. The first derivative 1, the second derivative 0, the third derivative negative 1. The fourth derivative 0, the fifth derivative 1, the sixth derivative 0, the seventh derivative negative 1. And you can keep going along in this pattern. Knowing that, plugging these things down here is not so hard. We get this. P7 of x is equal to 0 plus 1 times x minus 0 plus 0 over 2 factorial x minus 0 squared minus 1 over 3 factorial x minus 0 cubed plus 0, the fourth derivative is 0, over 4 factorial x minus 0 to the fourth plus 1 over 5 factorial x minus 0 to the fifth plus 0 over 6 factorial x minus 0 to the sixth minus 1 over 7 factorial x minus 0 to the seventh. And what we're seeing from before is all of the even ones drop off. Right, there's 0, that's 0, and 0 here, and 0 here, and 0 here. So all we're left with are the odd exponents. And therefore, P7 of x is equal to x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the fifth minus 1 over 7 factorial x to the seventh. Or if you like numbers better than factorials, this is equal to x minus 1/6 x to the third plus 1 over 120 x to the 5th minus 1 over, I think it's 5040, let me double check that, 7 factorial, get 5040 x to the 7th. Now let's plug that into Desmos and see how good of an approximation that polynomial is to f of x equals sine of x. All right, let me bring that one in. Okay, so in this case, this is again f of x equals sine of x, whereas the polynomial here in blue, this is the 7th. I believe I did 7 here. Well, I wonder if that's 9th. I say that because this is trending upward, and a degree 7 polynomial with a negative in front should be trending downward. I'm going to guess I've done here the 9th of x. Or did I do the 5th? I wish I'd have known. I should probably, you know what? Give me 1 minute and I'll put the actual one on there. Yeah, that was the 9th. I apologize. Let me go back to the 7th. I apologize for the silence here. Okay. This here that I've drawn, this was actually P9 of x. Let's go down and do P7 of x that we just had a second ago. There we go. So here we have f of x equals sine of x, and in blue here this is P7 of x equal to x minus 1 over 3 factorial x to the 3rd plus 1 over 5 factorial x to the 5th minus 1 over 7 factorial x to the 7th. And if we take a look at that, we can see that polynomial is a pretty good approximation to the sine of x all the way until we get to, say, -3 to 3. Afterwards, it veers off right from the sine of x. And the question that we have, that we're going to address later on in calculus, is can I get a polynomial that's just exactly on sine of x, right, all the way through infinity? If I keep this going through infinity, do I actually get equal to the sine of x? We'll see.